Welcome back to the session. We are ready now for the second keynote, which will be delivered by Danila Chebrov from the Russian Academy of Sciences Geophysical Survey. And it deals with the 8.8 earthquake that struck Kamchatka little more than 1 month ago on 29th of July. And this is a remarkably large event, and we will be seeing a pre-recorded presentation, which will be followed by a live question and answer session. Please, let's leave the floor to Dr. Chebrov. Thank you.
Good afternoon, dear colleagues. Thank you for the invitation to deliver this brief presentation on the outstanding seismic event of this year, the Kamchatka earthquake of July 29, which has entered the top 10 strongest earthquakes of the instrumental era. In my talk, I would like to briefly introduce you to the Kamchatka monitoring system, which ensures a timely response to this event. Then, I will discuss preliminary data processing results and talk about manifestations and consequences of the earthquake. The results presented here are shared on behalf of the entire Kamchatka branch of the Geophysical Survey, as well as on behalf of a number of working groups in which I participate. The tsunami warning system, its seismic subsystem, was developed between 2006 and 2010, following the Sumatra earthquake. As the provided figure illustrates, its technical capacity is entirely insufficient for a region as vast as the Russian Far East. Nevertheless, its establishment initiated a process of digitalization, modernization, and integration of regional monitoring networks. For example, in Kamchatka, its operational functionality is ensured through integration with the regional observation system maintained by the Kamchatka branch. Currently, the seismic network in Kamchatka consists of 85 stations integrated into a unified data space. More than half are modern digital instruments, but well-known Soviet-era analog SM3 instruments remain in operations. In some cases, they have proven to be incredibly helpful for us. Most of Kamchatka is an unpopulated, hard-to-reach area. So many stations must be designed for extremely challenging conditions. Given these constraints, we were compelled to design a multimodal data acquisition system that utilizes all available communication channels, from satellite links to radio Ethernet connections. These channels are subject to stringent reliability requirements. This slide shows a typical field station in Kamchatka. The stations are hard to reach, often accessible only by helicopter, so we must make them extremely reliable. We have gained significant expertise in organizing such complex monitoring sites and data acquisition system. The processed data is stored in an information system, and the catalogs are accessible to all interested parties. We are currently working to make waveform data available, and in the foreseeable future, waveforms will also be accessible online. I would also like to mention an important mission of Kamchatka branch, providing expert support to various government authorities, primarily the government of Kamchatka and Emercom, in the field of earthquake and eruption forecasting. For this purpose, the Kamchatka branch of Russian Expert Council for Earthquake Prediction was established. The primary function of this council is to systematize data for earthquake forecasting and to develop comprehensive assessment. We even maintain numerous long-term and continuous observation and scientific research aimed at identifying precursors and developing forecasting methodologies. However, while the challenge of the earthquake prediction remains far from being fully resolved, another function has come to the forefront, providing expert support to decision-making process within the emergency control system. Specifically, this involves developing scenarios for the evolution of the seismological situation. Let's move on directly to the earthquake. You might be curious to know about how the system performed during the event and some of the lessons we learned. The Kamchatka network was in good condition when the earthquake struck. Only 11.5% of seismic stations were offline, with just one of these being of critical importance. The offline stations are shown in red in this picture. As expected, all velocimeters were order-driven. It was only thanks to the existence of our strong motion accelerometer network that we were able to process the event promptly. Here's a familiar sight, perhaps to many: the order-driven channels. Stations at epicentral distance well over 1000 kilometers were also overdriven, such as those in Yuzhno-Sakhalinsk and Yuzhno-Kurilsk. And a few more words on how our tsunami warning system performed. The initial earthquake parameters were obtained within 5 minutes of the origin time. These were determined before the rupture process was complete and naturally before the shaking had stopped. Although the magnitude was underestimated, the unconditional tsunami alarm was declared for entire Kamchatka coastline. A more realistic magnitude estimate appeared only after 10 minutes. It was about 8. After about 15 or 20 minutes, we received a moment magnitude estimate from our colleagues. A heartfelt thanks to them for this. Around an hour in, the focal mechanism solution was obtained. We were unable to promptly produce our own estimates because our original data processing methodology proved unstable under conditions of widespread overdriven channels. Data collection and selection took a considerable amount of time. In this case, real-time availability of global data was a great help. Once again, many thanks to the United States Geological Survey. Importantly, the simple unconditional alarm protocol saved a significant number of lives. The most destructive tsunami impact occurred at the port of Sever-Kurilsk, yet all people there were saved. Here's a brief overview of the tectonic settings and seismic history of the region. You can see a major rupture zone of the last 100 years. Marked in green are the rupture zones of the recent Kamchatka earthquake and the preceding earthquakes over the past few years. All these recent events occurred after a period of intense seismic quiescence in Avacha Gulf and southern Kamchatka. A common topic now is discussion about the similarity about the 1952 earthquake and the latest event. Indeed, the ruptures area are very similar. On the map, last area is outlined based on the all aftershock cloud, while the old area is outlined only based on the strongest aftershock. At the time, there was only one seismic station in Kamchatka. Apparently, the big rupture zone has ruptured again after a relatively short time, which is a fascinating fact for all seismologists interested in the largest seismic event. Regarding the tectonic context, this is typical subduction-related mega event of planetary scale. An intense aftershock sequence is ongoing. developing in accordance with empirical laws. Over 20,000 aftershocks have been detected, with approximately 4,000 processed. The strongest aftershock had a magnitude of 6.9, and we believe there is a deficit of strong aftershocks. Currently, in our opinion, an aftershock with magnitude up to 7.5 can be expected. Our methodology for determining focal mechanisms did not allow us to quickly obtain the mechanism of the main shock. However, the mechanisms of aftershocks are being determined very rapidly and reliable. Almost all of them are standard. Nevertheless, they await the full processing of the aftershock sequence, which will provide interesting material. We hope to produce a catalog of mechanisms down to lower magnitudes that is typical possible with seismic data processing. Let's discuss the consequences of the earthquake and the seismic impacts. The pattern of impacts based on instrumental data in general matches expectation. And looking ahead, it corresponds to what we anticipate from the full macroseismic survey. The macroseismic survey is still ongoing. Most importantly, all buildings withstood the event. Only one building sustained fatal damage, a kindergarten, that was under major renovation and was unoccupied at that time. The main challenge is that the vast majority of the damage is hidden. We cannot independently assess the shaking intensity without the official inspection results. Until we receive them, they can formally only state that the intensity in Petropavlovsk-Kamchatsky and in nearby settlements was no more than 6 points. However, cooperation with the Kamchatka government has been established, and our experts are now receiving the inspection data. They are almost certain that Petropavlovsk can be assigned an intensity of 7 points. The maximum impact were recorded in Sever-Kurilsk. The earthquake-resistant construction performed excellently, and shaking was perceived as reaching 8 points. Finally, regarding the tsunami impacts, a rather large working group, those members are listed on the slide, is handling the task of data collection and study. Surveying the Kamchatka coastline is extremely challenging, yet it must be done quickly before the end of the field season. Nevertheless, I can show you some very preliminary results. Here in the picture are some data of tsunami run-up heights. I took on the role of an expert and drew smoothed line to show how the run-up heights were distributed along the coast. Importantly, we observed a local minimum precisely in the Petropavlovsk-Kamchatsky area, which coincides with the most dangerous spot, Halaktersky beach. This is outside the city, relatively wild area, so there is no warning system here. Moreover, tourists tend to seek out remote area away from civilization. During the warm season, a large number of people are always present in the tsunami hazard zone. Here, the tsunami didn't even overtop the storm ridge. Thank God there is nothing more to say. All these specific manifestations of the earthquake are explained by the slip distribution of the fault, and of course Doppler effect. As here we see a classic case of unilateral rupture propagation from north to south. Here is a well-known model obtained by the United States Geological Survey based on teleseismic data and INSAR data. Colleagues have already significantly refined it, incorporating 3 fault planes with varying deep angles. A large Franco-Russian group is working on a model based of GNSS data and strong motion records. Here is one of the preliminary results. And we can see here not only heterogeneous slip distribution, but also a regular shape of the source area. Finally, the group led by academician Mikhailov has developed a model based on local displacement data and the INSAR data. This is also an interesting and quite complex model, incorporating 4 planes with varying deep angles. All the models shown share similar features in the slip distribution. The maximum slip is located on the southern flank of rupture, while the northern flank exhibits a relative deficit. Kamchatka has successfully survived one of the strongest events in the history of instrumental observations. Most importantly, buildings and structures proved to be prepared for such shaking. In my opinion, there was a significant element of luck in this situation. I have listed many positive factors here. For example, the fact that the event occurred during daylight hours alone ensured more efficient response from the emergency control system. As for negative factors, such the powerful flow of fake news, they ultimately didn't lead to the fatal consequences. For this, we remain grateful to the Almighty, and you, dear colleagues, thank you for your attention. Спасибо.
This very interesting presentation. We realized that the author is unfortunately not connected because of connectivity issues. He is in the Far East in Kamchatka, and it is possible that the connection may not be working well at this time. We are fortunate that we could receive the pre-recorded presentation, so we're very thankful for that. And therefore, I don't think we can ask any questions, Monica.
No, but the questions still can be posted in the chat of the app and of the virtual platform, and we'll transfer them to the presenter. So once more, thank you very much, Chen Ziwei and Danila Chebrov, for the presentations regarding the most recent earthquakes. And with this, we close the session of the first 2 keynotes of the SNT 2025.
Thank you, and we now leave a few minutes. Bear with us so that the technical experts can reconfigure the link and then connect you to the online session. Thank you very much.